All right, so we're going to continue with chapter 10, hypothesis testing. And today we're going to look at the results step. So these are like my calculations, okay? So what we're looking at is how does our sample compare to the common view? Remember, the common view is my null. Okay, that's what we're looking at. So I'm going to break this into the two different types of data just because everything's really the same, but the numbers you're plugging in and that kind of thing just changes. So we'll take a look at numerical variable first. So meaning if my variable is numerical, meaningful number, and we're studying means in that case. So we'll take a look at that first. So I want just to remind you here, we are studying the t-curve when we're looking at numerical data, and the t-curve changes shape with degrees of freedom, which is n minus 1. Okay, just like to keep in mind what curve we're studying, so we're going to start looking at that today. So for my numerical variable, for my result step, I have 4 parts for either type of variable. But the very first one, we're going to calculate the t-test statistic. Okay. So my calculation for this is just t is equal to, and this is gonna look really familiar to you, x bar minus mu naught divided by standard error. Now, when I say this looks familiar, this should look like z, right? Remember z-scores back in chapter 3, it was x minus the mean divided by the standard deviation. It's the same calculation, right? It's just now I'm looking at my whole sample, x bar minus mu divided by the standard error. So x bar is my sample mean. I'll write all this to the side and we'll talk about what this mu naught is. This is similar to p naught for categorical data. And my standard error is s divided by the square root of n. So I just want to plug that in there. So when I remind you what this means, so this is going to be the number of standard errors away from the center of the curve. The center of my curve here is mu naught. That's my center. Okay, so let's talk about what these represent. So x bar, this is my sample mean. Mu naught is the center of the curve. This is from my null. So remember last week we talked about p naught, and I said it was the center of my curve. It's from the null hypothesis. The same thing here for mu naught. It's just now I'm looking at numerical data. Okay. And then s is the standard deviation, and for my sample, and n is my sample size. Okay. So we're going to first calculate the test statistic. That's my very first part of my result step. And then from there, I'm going to interpret what that number means. So I'm going to get a number like maybe I'll get like -2 or negative 1.56 or something like that. Okay. So I'm going to get a number here. And it's telling me how far the sample is from the center of my curve. So I'm hoping you guys can kind of visualize that as I say it. It's telling me how many standard errors my sample is from the center, mu naught. Okay, so when we interpret it, that's all we're going to say. I'm just going to say, okay, we're going to interpret the t-test statistic. So we calculated it, and now we're going to interpret it. And I'm going to write like a blanket interpretation. You're welcome to use this, or if you want to write it your own way, but it's pretty simple. And I end up kind of abbreviating as I move forward, but just so you know. So I'm going to say our sample mean, I'm just going to put in parentheses X bar so we know it's X bar, is whatever my test statistic came out to be. So I'm just going to put absolute value, my t test stat. And you'll see why I'm going to use absolute value of that. And so that many standard errors above or below. Now this is why I'm using the absolute value up here, because here I'm going to address above or below. So if my test statistic by itself is negative, then it means it's below my center, right? And if it's positive, it means it's above the center. So I address that positive or negative. So I just write it as a positive up here, but I address that right down here. We're saying above or below, and I'm going to put my center of my curve. So I'm going to write mu naught and then center. And you know what I end up doing? I make it so short. I end up saying, sometimes I say my X bar is 1.56 standard errors below whatever my center is of 5 or something like that. And you can see it's like a quick, short statement, but it's the point of just stating what this number represents to us. It's just how far I am from the center based on my sample. So how far my sample is, okay? And that's what we want to do. We just want to make sure we put it into words so we understand what it is, okay? So that's the second part of my result step. Now the third part, this is not anything new for us, just like the test statistic, really that calculation's not really new, and this is going to be calculating the probability. So I'm going to calculate the probability that my t value is either, I'm going to put in here greater than or less than, okay, my other t value, which we'll take a look here. And I just want to write here that this, I guess I'll write it below it. This right here, this matches the HA. So if your HA, excuse me, in your method step is a less than, you're calculating a probability that's less than. If your HA is a greater than, then it's greater than. Now, when it's a not equals, that's tricky. So when HA is not equals, then we'll talk about how to calculate which one, the less than or greater than. And that's where my, that's where the pictures come into play here. So let's just talk about this. This is called the p-value. Now, when you start looking at your book or your homework, you're going to see it's called the p-value approach, and that's how we're making this hypothesis test work. We're using a p-value. A p-value represents the probability. That's it, okay? So the p-value is the probability. Let me just write that, equals probability. The way we're going to calculate this is, think about it, we're on the t curve, right? T, so we're going to use our TCDF function. So in Minitab or on our calculators, and on our calculators, and I just really like to mention it either way, but you have to put your lower bound, and this is where the drawings come into play, your upper bound. So very similar to a normal CDF. It's just you're telling your calculator or Minitab to use T curve. And then here, for this curve, we use degrees of freedom. And degrees of freedom equals n minus 1. Because remember, my T curve changes shape based on that. So we use our lower bound, upper bound, and degrees of freedom here. Let's just take a look at some pictures. The pictures are really helpful. This visual just helps us organize like what we're really calculating here. So remember we have 3 scenarios, right? Let me draw out my curve. So my first scenario, I might have a greater than. Okay. And what we're calculating is we're calculating this area greater than my value right here. Okay. So this is my t, test statistic. And I'm calculating the area to the right. So this right here is my p-value equals the probability right here, that area in the curve. So what this is saying is this is the probability of getting a value of t or greater than t. So think about back when we're just looking at the normal curve and we start calculating these probabilities under the curve and the area. If we had greater than, it meant that it's going to be this value or larger, right? And it was the probability of getting that. And that's all we're doing here. So this is not new. This is taking what we already know and now we're applying it to something different. But I say different, but it's not really different. So we're still looking at the probability of getting a t here or to the right, greater than. Okay. Now, if we have a less than, let's see where I want to put this here. Maybe I'll stagger these. Okay. My less than, this would be a t, and I would be, sorry, I'm not up here, calculating the area to the left. Okay. Maybe I'll just put that here. HA is a greater than. HA would be a less than symbol. Okay. And we're calculating this. This is my p-value equals the probability of getting a value of t or smaller than t. Okay. And that's what we're calculating. Now, here in the last scenario where I have my curve, and maybe it's a not equals. So maybe we're looking at both sides. So we have to the left and to the right. What's tricky about this, so for this case, when we have HA is a not equals to where it says it's different, my sample, which is t, my t-test statistic, will either be here or it will be here, right? It will either be up here or up here. So it depends. If my sample is greater than my center is mu naught, and all of these, let me put that in here. Then I'm going to calculate the greater than. If my sample is a negative number and it's below my center, then I'm going to calculate the area to the left, a less than. So for the not equals, you have to pay attention to where your sample is located to in comparison to your center. So you get it right here, right, from your test statistic. If it's above, it's greater than. If it's below, it's a less than calculation down here. Okay, so it should all roll right together. Draw a picture if you need help. You're not ever going to just be given a test statistic down here and then calculate this whole probability up here. You wouldn't be getting that. So you should never really be calculating a probability that's greater than 50, 60%. That's not really what we're looking at. It's normally these little calculations here. Okay. And what I need to mention about this not equals, so I want to kind of separate this out. So if HA is a not equals. We calculate, oops, the p-value for one side, right? So if my test statistics up here, I'm calculating this orange area up here to the right, but I didn't calculate it for here. But it's symmetric, it's the same. So we need to multiply the p-value by 2. So we want to make sure we use both sides and not just one side. See, if we're up here with just a less than, you only have one side. Or if you're up here in the greater than, you only have one side. You don't have to worry about it. But on the not equals to, it's a little trickier situation. First, I have to figure out for on the upper or lower end, calculate that area in the tail, and then multiply by 2 to get my true p-value. Okay, and that's what we're going to look at. I want you to think about it when you're doing it by hand, like we're doing the TCDF. That's when you multiply it by 2. If you're using technology, you do not have to multiply by 2. So I'm going to make a note of that, and I will type this up in a when I give the instructions for Minitab and give the instructions for the calculator, so we know. So I'm just going to say not if using technology. So just mean if you're using technology to calculate these p-values, you do not need to multiply it by 2 because it will do it automatically. Okay, and we'll get to that. Well, I'll demonstrate doing all this with technology at some point. Maybe I could do that next class. Okay, I'd like to give you these visuals. You guys don't hesitate to draw these real quick and sketch it out. So you got your t-test statistic, you just found it. Don't hesitate to draw where it is on your curve, okay? Don't hesitate. Okay, so when you're on, I don't really know what I want to use here, like a pen or something. So when you're on your now t curve, your center is now at 0, right? And your t-test statistic is right here, okay? Same thing down here. If you were on the t curve, your center is now 0. It's like standardizes everything. And here you're at your t-test statistic. Same thing down here. It brings your center to 0. Okay, we're not actually plugging 0 in because just by using TCDF, your calculator or Minitab knows that. I like to let you guys know all of that. Okay, so now once we calculate our p-value, so we find this area, we want to interpret what that means. So this interpretation can be a little tricky for most of us, and we just kind of get used to it. But I'm going to write it out, and then we'll just kind of talk about what it actually means, like what this is for us. So I want to make sure I'm using the right notation. Interpret the p-value. All the p-value is the probability, okay? So when we interpret this, again, you can use this blanket statement or you could write it in your own words if you want. So if the population mean equals mu naught. So if the population mean is the center of my curve, that's kind of what we're basing this all on, right? That's my common view. So if that's true, then I'm calculating my p-value based on that, right? There is a p-value probability of getting a sample mean at least as extreme as the one we got from sampling. So let's think about what that means. So when I'm interpreting this p-value, it's my probability. So I'm saying, first of all, if the population mean equals the center, so if the center is true, okay, then remember, I'm calculating my test statistic based on that center, right? So now on my t-curve where the center is 0, my t-test statistic, I'm calculating that probability. So that's all this is stating, is that if the center is whatever my mu naught is, okay, then I found a p-value. So whatever it is, this area under the curve. And what that says is just what I said up here. It's the probability of getting another t-value at this point or beyond. So here or greater than, or even here or less than, okay? So all I'm saying is it's the probability of getting another sample mean, at least as extreme as, so meaning this far away from the center or further. That's what at least as extreme as means. Then we got from our first sample. So what I'm saying is this is the probability, my p-value is the probability of getting a second sample that far away from my center, or a third sample that far away from my center, or a fourth sample, right? That far away from my center. So based on mu naught being my center, my p-value is my probability of taking a second, third, fourth, fifth sample, however many. Okay, so getting another sample that far away from the center as this one was. That's all it is. That's all my p-value is, okay? So it's the probability of getting another sample that far away. So the whole idea behind this p-value approach is that if the probability is really small, so my area over here is really small, then maybe my common view, my mu naught, shouldn't be the center. Maybe that shouldn't be my common view anymore. And that's really what we're saying. So that's what's going to happen here. Next class, we're going to look at this p-value and say, well, if this is really small, then maybe the center isn't the center, because why am I getting a sample so far from the center? Maybe that's not really the center anymore. And that's what we're saying. So that's the 4 steps for my numerical result step. So let's take a look at the categorical. It will go a bit faster because I don't have to write everything all out again. It's really the same thing. So we look at our categorical variable. Remember, this is when I'm studying p, proportions. Okay. So here we are on the z-curve. Remember, the z-curve has a center of 0 and a spread of 1. So we're going to do the same thing that we did before. We're going to calculate the test statistic. So here, we're going to calculate the z-test statistic. So it's going to look like a very similar calculation. It's just now what I'm using, I'm calculating z. So and it's categorical data. So what I'm using to plug into this calculation is a little different than for the t-curve. So z is equal to my sample, so p hat, minus the center of the curve, which is p naught, divided by the standard error. So I'm going to fill that in here. So it's p hat minus p naught divided by the standard error. So remember last week, I mean, it was a while ago now, 5 days ago now, but we talked about p naught. P naught is the center of my curve. And remember, we talked about checking normality. And when we do that, we use the center of our curve. Think about standard error. We do this also using the center of our curve. So my standard error formula is the square root of p times 1 minus p divided by n, right? But p is not the center of my curve. P naught is. So we want to make sure we use our p naught value there. Okay. So I'm going to write these off to the side just to remind us. P hat is my sample P. Sample proportion. P naught is the center. This is from my null, okay? And then my standard error, and N, of course, is my sample size. So the next thing I want to do is interpret the z-test statistic, same as numerical, but now it's about proportions. Excuse me. So, like numerical. So now instead of saying my X bar, I'm going to say my P hat. So my P hat is this many standard errors. You know, I start abbreviating above or below my center. So it's my absolute value of my z-test statistic. Standard errors, and it's above, meaning my test statistic is positive, or below, meaning it is negative, my center. And the center here is P naught for my categorical data. So there's my interpretation, cut down and abbreviated. Feel free to cut it down and abbreviate it like that, okay? I just want to make sure you understand what that number represents. That's the whole point of it, okay? Then after that, we're going to calculate our p-value again. So the probability of getting a z either less than or greater than my z-test statistic. Okay, that's what we're looking at. This is my p-value. Here we're going to use normal CDF. We have normal CDF. Of course, we're going to include our lower bound, upper bound, and then we're on the Z curve, 0 for center and 1 for spread. Okay. Then next we want to interpret that p-value. And it's the same way. But it's, instead of saying the population mean and sample mean, I'm going to say the population proportion and sample proportion. Okay. Let me underline some of these things to separate them out a little bit. So if the population proportion is, and I'm going to have P naught here. There is a p-value. Probability of getting a sample proportion at least as extreme as the one we got from sampling. Okay, so the same meaning. It's the probability of getting another sample that far away from my center as I did from my original sample. Okay. So this drawing still are the same. Instead of Z, we're looking at T. Okay, so it's really very similar. So we've got about 10 minutes. I want to go through these two examples that we started last week. So the first example from last class, and that was about the support of, let's see, student support of the university's administration. Okay, so that's example. So I'm going to write some information down for us to recall. So we're going to recall our null and alternative hypothesis. So our null was that our P is less than or equal to 0.67 because our HA was that the professor wanted to prove the population proportion of RIT students who support university admin or approve of it is greater than 67%, right? Okay. And remember, you can always write this as P is equal to 0.67. Just like to remind you of that. Okay. So our sample, we had 80 students in the sample, found that 62 answered yes. So that left us with a p hat of 62 divided by 80, which was 0.775. Okay. We did check for normality, right? And we used n times p naught times 1 minus p naught is greater than or equal to 10, and it did check out. Okay. So now let's take a look at our results step and how we're going to write these. So for our results, I'm first going to calculate that z test statistic because it's categorical, right? I'm using p's here. That's proportion, p hat, my sample proportion. So that means I'm on the z curve. So let's just write that down just so we all remember. Remember, we would know this from our first step. Remember, the second example is numerical. Okay, so here I'm going to use my z equals p hat minus p naught divided by the standard error. So I'm just going to plug everything in. So p hat is 0.775. P naught is, remember from my null, 0.67. My standard error, I use the value from p naught, that 0.67. So the square root of 0.67, 1 minus 0.67, divided by n, which is 80. I'm going to calculate this out, and I get 1.9973. So now I want to interpret this 1.9973. So this is where I am located on my curve. This is how far away my sample, which is the 0.775, is from the center, 0.67. So it's not just how many units, it's how many standard errors, right? So I'm just going to say my p hat is 1.9973 standard errors above 0.67. Done. Okay. So it's like a real simple explanation how far it is. You can write it any way you want as long as you get your point across that it's that many standard errors above or below your center. Okay. All right, now let's calculate this p value. So now I need to go back and look at my HA. Remember, I always said it's to match your HA. The tricky ones when it's not equals, and you really need a picture for that. I'm definitely going to draw a picture because they always do. It's a greater than, right? So I know I'm calculating the probability that z is going to be greater than my test statistic, 1.9973. But let's draw a picture to just kind of have that visual, right? Let me grab another piece of paper for that. Well, maybe I can just do it over here. I hate to have it separate. I'm going to draw my curve. My test statistic. It's this 1.9973 above, right? So it's positive. So it's over here, 1.9973. When I'm talking about the z, now I'm on the z curve. So my center is 0. Okay, if you're looking at your regular curve, then your center is 0.67, and this would be the 0.775. Okay, I'm calculating greater than, calculating this area. So you can see what your lower bound is, 1.9973. Your upper bound is positive infinity. Center is 0, spread is 1. So I'm just going to plug that in to my normal CDF. So 1.9973, 10,000, infinity, whatever you want to use, 0 and 1. So I find that this probability is equal to 0.0229. So what I'm saying is this area right here in my curve, 0.0229. So I have a 2.29% probability of getting another Z value, another sample that far away from my center. That's what that means. So let's write that out. This is like the fourth step. I can kind of back that off. Okay, so this is now the fourth step. So if the population proportion is equal to 0.67, remember that's my P naught, the center of my curve, there is a 0.0229 probability. I leave it in decimal form, of getting a sample proportion, meaning, so another one, at least as extreme as the one we got from sampling. Okay. So what this is saying is I have a 2.29% probability of getting a second sample proportion this far away from my center. Okay, this far away. That makes sense to you guys? So that's my results. So let me see. Let me check out what time it is. All right. 3 minutes. All right, let's just do it. I was trying to see if I want to do the next one. I do. I want to keep it with this. Okay, so this was the apple problem real quick from last class. And just to refresh your memory from last class, we had our null was that the mean is greater than or equal to 6 ounces in the HA. Remember, so it was this this grocery store manager, and he believes that his apples are less than 6 ounces. Okay, so we want to test that out. So here we're on the T curve, right? And we have an N equal to 61. We found X bar equal to 5.6 and S equal to 0.1. So that's all the necessary information I need to move forward, other than normal, because N is greater than or equal to 30, right? So here for my results step, I need to calculate my test statistic. So my T test stat is equal to my sample mean minus the center divided by the spread. Okay, so it's X bar minus mu naught divided by the spread is S divided by square root of N. I'm going to plug all my values in. 5.6 minus 6 divided by 0.1 divided by the square root of 61. Just plugging everything in. Okay, so I find this to be negative 31.24. Negative 31.24. You guys, this is a huge number on the negative end. Think about way back when we were looking at empirical rule. We said anything that was more than 3 or 2 standard deviations away from the center was unusual. Think about it if you're 31 standard errors away. It's 31 standard deviations away. That's far. That's really far. Okay, so I already know my p-value is going to be small, right? The probability of that happening again is going to be really tiny. Okay, I'm just visualizing. So let's just write out what this means. So my X bar is 31.24 standard errors below, because it's negative, my center of 6. Okay. Let's calculate that probability. If you want to take a look at a picture, you could do it first. Sometimes it's helpful for people. So I'm looking at negative 31.24, and I'm calculating this area down here on the left. So I'm looking at the probability that T is less than negative 31.24. Okay, so here I'm using TCDF. My lower bound is negative infinity or negative 10,000, whatever, and up to negative 31.24. And then remember, I need degrees of freedom. That's n minus 1, n is 61, so 60. So I plug that in. It looks like you have 0.00. This is not really 0. It's not really 0. Okay, so here we call this very small. To say that you have a 0 probability, that means it will never happen. It just did happen once, right, in our first sample. So you never want to report 0.00 as a 0 probability. You want to report it as a very small probability. Okay, so it's not really 0. It's very small. It just means we don't have enough decimal places to show it. That's what that is. Okay, so real quick, I just want to write my interpretation so we all have that. So if the population mean is 6 ounces, there is a very small probability of getting a sample mean at least as extreme as the one we got from sampling. Okay, same interpretation. I want you to see I use very small. I never use 0. Okay. All right, guys, so that's my results step.